Everyone, my name is Nick Olson. I'm a third-year PhD student, currently advised by Professor Andrews and Professor Heath. And today I'll be presenting my work concerning the coverage performance of terahertz cellular networks in the presence of imperfect beam alignment. So the terahertz band is a promising spectrum for beyond 5G and 6G cellular networks due to the great availability of bandwidth in that part of the spectrum. But there's some challenges here in that since the frequency is much higher than those conventionally used, dispersion losses are a significant phenomena. And to overcome them, very narrow beams or highly directive antenna patterns are required. The usage of these narrow beams, though, poses a challenge in terms of beam alignment and tracking. As the beam widths become narrower, the probability of beam misalignment becomes higher. So given the trade-off between these two features, one may wonder how well terahertz cellular networks can perform in terms of coverage. And this is the question that we address, and we do so using a stochastic geometry framework. So stochastic geometry is a tool that's been widely used to analyze cellular networks for quite a while now, and it's been used in a variety of settings. But past work hasn't really considered the joint problem of coverage in terahertz cellular networks and the problem of beam misalignment specifically. So this is sort of the gap that our work fills. It's also notable that our work has some slightly more tractable results than past work. So this figure here sort of demonstrates the model that we're considering. The coverage probability may be defined as the probability of the SINR of a typical user in the network is greater than some threshold. And the SINR itself is a function of the spatial distribution of the interfering base stations, the effect of random blockages in the network, partitioning the channel into either a line of sight channel or a non-line of sight channel. It's of course very tightly linked to the channel modeling considerations, both with respect to the fading distribution and the path loss expressions. Specifically for our work, it's important to consider the overall antenna gain for the desired signal and the interfering links, as well as the phenomenon of beam misalignment for the desired signal. And then finally, it's also a function of the user association policy, the policy by which the typical user is mapped to one of the base stations in the network. And stochastic geometry provides a sort of a key analytical framework for capturing this. So to state this more formally, the SINR may be expressed like this. The numerator here is a function of the choice of the fading, H, the antenna gain, Z, and then the path loss, L. The path loss is actually a random variable due to the fact that the desired signal may or may not be line of sight or non-line of sight. And we have a similar expression for the interference term, which appears in the denominator. And of course, the noise variance is important to consider. And for the expression here, the noise variance gamma is normalized by both the transmit power as well as the main lobe gains. So there's a lot of notation here, but this is the main result of our work. It's a lower bound for the coverage probability. Unfortunately, I don't have time to go into the derivation, but there's a few tricks we use to get this lower bound. First is that we homogenize the base station process into a process that can be treated as if all the base stations are line of sight. And this sort of simplifies the path loss expressions in the SINR model. We also exploited some of the features of the interference, mainly the fact that it's dominated by line of sight base stations, to get a nice lower bound for the Laplace transform, which characterizes the interference process. And putting these two together, those are sort of the key ingredients for deriving the lower bound. Basically, using this result, we can now gain some insight into the performance of terahertz cellular networks. So this figure here depicts the coverage performance of a terahertz cellular network with and without the effect of beam misalignment being considered. And we show this for both simulated results and with the analytical lower bound that we derived. And you can see that the lower bound that we derived performs pretty closely to the simulated results. And also beam misalignment is a significant feature. At the 90% coverage level, there's a 40 dB difference in performance between the two, which is quite significant. So to conclude, in our work, we have modeled a terahertz cellular network that considers the effects of beam misalignment, and we've used this model from a stochastic geometry point of view to derive a lower bound on the coverage probability, which is pretty tight. And then using this lower bound, we're able to investigate the performance of a terahertz network numerically and be able to confirm that indeed beam misalignment is a significant concern, and also dense beam base station deployments are required to achieve sufficient coverage given the strong impact of both blockages and beam misalignment. So that's my presentation. Thank you.